Hello and welcome to a brand new video on the sodium-potassium ATPase pump or sodium-potassium exchange pump, whatever it is you do prefer to call it. And what we're going to be talking about today is two major themes. We want to discuss the basic function of this pump, and we want to discuss its cycle. Now, in the background, the titles here, you can actually see protein structure and the many different protein subunits involved in this complex pump. So it has a very complex three-dimensional structure that's going to allow it to do the job that it does. And we're going to simplify it in a few different ways. And we want to start off with just basically, what is this pump? Now, this pump is the absolute most important active transporter. So this is an active transport. Now that means if it is active transport, that means it will use energy, usually in the form of ATP, though there are some active transports that use electrons. But ATP is going to be the major thing here. So what this cell is going to do, this pump is going to do in any kind of cell that has it, and all cells do have a sodium-potassium ATPase pump, is this pump will be embedded in the cell membrane, and it will be pumping, as its name implies, sodium and potassium using ATP energy. Now it is an antiporter as it transports in opposite directions two substances at the same time. So it will bring in two potassium cations and pump out three sodium cations for every molecule of ATP expended. And that will end up producing ADP and an inorganic phosphate molecule from that. So it's going to be that phosphate that's important in phosphorylation of the ATPase. So now when we look at this, we understand that there is far more, a very high amount of sodium cations in the extracellular fluid, in the ECF. And in the intracellular fluid, there is going to be a fair amount of potassium. And that means there will be a low sodium environment after the pump is pumped. And in the ECF, there will be a low potassium environment. And what we have done here is created a chemical gradient. And this chemical gradient is a difference in chemical concentrations of various ions in the ICF and in the ECF associated to this cell. And because the ECF has such a high amount of sodium, which is 3 sodium cations, there will be a lot of extra positive charge out here. So the ECF is going to gain a considerable positive charge, where the ICF, who has less cations in, because we are only bringing in 2 potassium cations, the charge is relatively negative. It's a relatively negative charge. It's usually around about negative 90 something millivolts for some cells to negative 70, for example, like neurons. So you're looking at a fairly negative charge. And what we would say is this cell has a polar charge, or polarized. So this cell, this maintains the resting membrane potential of an active excitable cell. So this is the overall function. Now, biochemically, as we showed in the little title slide here, that the protein has a multiple polypeptide chains involved in it, each of them different subunits with a complex three-dimensional structure. What we're going to do is take our small circle and now kind of expand on it and draw it in kind of 6 different steps, and we're going to draw it in a very simplistic form and help us understand what's going on. So what we want to do is picking some colors here. We'll use blue to draw the protein in. And we're going to start off with step number 1, and we'll describe what's going on in the very first step with this protein. And this protein has a unique structure. Now, how we're going to draw this structure is on one side here, I'm going to draw kind of a little bit of a half moon shape with some triangles cut out of it on one side. And on the other side of the half moon, we're going to put 3 little circular bits cut out of that. And so this protein being embedded in a cell membrane, let's draw some phospholipids, since we want to make sure we understand that this is in fact embedded in the phospholipid bilayer in the plasma membrane and the cell membrane. And let's draw our fatty acid tails, just so we have a basic understanding of what's going on here. Now, because the ions that it's transporting are hydrophilic, they are not lipid soluble, and they must go through the cell membrane using a protein. Now, this protein here, this pump, is functionally, it is open to the inside, to the ICF. So over here will be the ECF, the extracellular fluid. And this pump has a structure that has it open towards the inside, having it in a state that will have a very high affinity for intracellular sodium cations. So the sodium cations, the Na pluses, because this protein has such a high affinity for them, will bind to these little sodium binding sites on the protein. We're drawing them thusly, that is not the real structure of it, but they will bind to this, and it will bind to 3 of them. Now, the very interesting thing about proteins is oftentimes when charged particles or other substances bind to them, it will shift the bonds. A lot of times there will be, for a great example, is highly charged arginine residues will cause shifts into the chemical structure, changing its shape. And that's what we're going to see coming along, is binding of certain substances will cause shapes to change. So the first conformation here, our second step of the pump, step number 2 that we want to look at, the pump is still going to be in its same shape from before. So we want to draw it in the same basic structure. And again, with its 3 sodium binding sites. And it had its high affinity for sodium cation. And the sodium cation binding to it is also going to be actively changing the structure and stimulating the hydrolysis of ATP. ATP is produced by the cell all the time. So if ATP in the cell is going to be hydrolyzed, what is going to happen is you break it down into ADP, adenosine diphosphate, and also an inorganic phosphate. And this inorganic phosphate will be stuck onto the surface here, and we say that it's been phosphorylated. Once that phosphorylation occurs by sticking a phosphate, phosphorylation acts as an energy, which is going to dramatically change the structure of this protein. And that's what we're going to see in step 3. So let's just quickly sketch in our phospholipid bilayer here for neatness purposes, and let's continue. So I hope you kind of draw with me and go through this and make notes. It really can help you understand the concepts better. So now that we've done this, what we next want to do is this phosphorylation will change the structure, changing the shape. That's why it's an ATPase. And we're going to see what happens here for step 3. Now in step 3, as we said, it's going to change the shape. And the shape is going to shift out to open up to the ECF. So we're going to take this protein and we're going to draw it like this, opened up to the ICF, to the ECF, sorry. And we want to draw our 3 sodium binding sites. We've changed the conformation. Why that is it was phosphorylated by this inorganic phosphate that shifts the shape. So let us draw our cell membrane here, making sure we know what it is that's going on here, where things are. And we really here need to make sure that we put our ECF and our ICF here. So our ECF, extracellular fluid, our ICF, our intracellular fluid on the inside. So the protein shape had changed in such a way that it shifted it out to the outside. This phosphorylation not only changes the structure of the protein, but its affinity for sodium is depleted. And what's going to happen is all this sodium is going to get released to the ECF as the affinity decreased because of phosphorylation. We release it. Now, eventually, this conformation here is going to, this release of sodium cation here is going to help result to the 4th thing that happens with the pump. So in step 4, what we want to pay attention to here is this pump having been phosphorylated and then releasing sodium. The sodium's release and the outward conformation, after it loses sodium, it will gain affinity for potassium. Now, what we want to make sure we are doing is it is still open to the ECF, so we want to have it open thusly. We still want to put our 3 little sodium binding sites. Sodium has been off there. What is going to happen? This conformation is going to increase the protein's affinity for potassium ions. And when it does this, we're going to see what happens with the ECF and the ICF. Okay, so let's make sure we do put our ECF and ICF. We want to have our ECF located here and identified. We want to have our ICF located and identified. And we want to show that this protein here, once this happens, the potassium affinity goes up and it will bind to potassium binding sites on that protein, somewhere in that protein. It's in there somewhere. We're going to get into it, but this is a model to help us understand it. Now that affinity, as that binds, will then change and cause this protein to release that inorganic phosphate. Now that this pump is no longer phosphorylated, as you're guessing, its conformation will change. And that's where it's going to take us to step 5. Step 5 is going to see a change in conformation back to how we've already seen it before, back to where it's going to be opened to the ICF again. So the conformation of this protein shifts and opens back up to the inside. So what we're going to do is draw our phospholipid bilayer yet again, putting those fatty acid tails in there, our cell membrane, plasma membrane. We want to make sure we have that so we know what's going on. Once again, we want to go in and put our ICF and our ECF, ICF here, ECF there, so we know where the fluids are. Now, it is still bound to by potassium. It's holding on to it. It's still got a high affinity for potassium. When it goes, when potassium is lost, it goes back to its original conformation, but it is holding on to that potassium. Now, what is going to happen at step 6 is where this protein, now that it has changed conformations, that conformation, after being in that conformation, will start to change its affinity for potassium. And this is quite important, as you can tell, that these affinities for things are changing depending upon what binds to this protein. So this protein here, this pump, let's again draw a phospholipid bilayer because we want to make sure we know where everything is, how this guy works. So let's again put our ECF and our ICF here. And what's going to happen in this conformation, the affinity for potassium diminishes, and the 2 potassium cations will now be released into the ICF. Now, eventually, after all this happens, the affinity for sodium will go back up, and we will go all the way back to step 1, where where it will pick up sodium. That sodium will then lead to the hydrolysis of ATP, phosphorylating it, changing its shape, and releasing sodium into the ECF. Then that will increase the affinity for potassium. Potassium binding will let go of the phosphate, which will put it back to its original shape. That then will release potassium and put it back to step 1. And this pump cycles thusly continually as long as you can supply it energy. And this is why, as we run out of energy, cells are going to not work very well at all. This is why when you start losing certain ions, it will influence the sodium-potassium ATPase pump cycle. Certain drugs like cardiac glycosides, things like what you would get like digitalis, digoxin, these are going to mess up the actions of these pumps and reduce heart activity. So very important that you learn this for pharmacology and pathophysiology. I hope you found this video helpful. If there's any other topics out there that you would like to see me do a video on, please comment, let me know. Don't forget to subscribe. Let me know what you like to see in future videos. And don't forget just to tell me what you think and what I can do to improve. Thank you guys so much for watching. I appreciate it.